guys. This is Rishi Polapale, and this is my Lab 1 Physics 2211 presentation. Okay, so to introduce the lab, we observed how an expo marker rolls down a flat platform with respect to time. The flat platform was our lab table, and we simply recorded a video of the expo marker next to a meter stick. And we compare the position over time using an observed model with the actual expo marker and a computational model, which we'll get into later. The purpose of the lab is to simply just recreate a common kinematic scenario of an object's position versus time. We use the computational model to compare what we usually see in physics problems under ideal conditions, which we'll also talk about later, with the observed model from the lab itself. So see some fundamental physics principles. Of course, Newton's first and second law, the first one being an object in motion stays in motion, and the second one being force equals mass times acceleration. Another one is net force, or the lack of. This lab assumes that there is zero net force, since we want to observe a marker with constant velocity to actually get a position versus time graph. Obviously, kinematic equations to base position off of time, and ideal conditions. Ideal conditions are what make the computational model so accurate and are what usually used in physics problems. That means no gravity, no air resistance, no friction, and no net force. The models used are the observational model and the computational model. So for the observational model, like I said earlier, we used an expo marker rolling down a flat lab table. The calibration points were actually set 30 centimeters apart from each other. What that means is that we used only 30 centimeters of the expo marker roll. This is because we wanted to capture the time where there was no acceleration, no net force, and constant velocity. The position of the marker was tracked using a tracker in equal time intervals over the whole period of calibration, and from this, a position versus time graph was created. The other model was the computational model. For the computational model, we used a Python program to predict the marker's position at any given time. We used the velocity that we gathered from the calibration point in the computational model to make some accurate predictions. The main physics idea is to simply estimate the ball's velocity and acceleration at any given time, and using those values to find the position at any given time, which is simply kinematics. Here's the graph that we did. As you can see, the blue one lies a little bit above the red one and has a little bit more irregularities. That's because the blue one is the observed position with some conditions that we cannot change, such as the initial push and the surface of the table. Why did we use this model? I used a line graph because of the amount of points that we had. If I used a bar graph or any other graph, that would be illogical. And it also shows the perfect linear trend that the both models exhibit, and it shows the irregularity in the observational model. The main assumptions we have to make is that the total travel time of the marker is 1.133 seconds. Although we know it's not true, we need to make this assumption because we need to gather only the time when the marker was under constant velocity. And also the marker was treated as simply a point in space, so none of its grooves or shape or the lab table shape affected its motion. And lastly, of course, there's no net force present. So some comparisons between both models are that the line of best fit of the observed model would lie right above the line of the computational model. They would both have the same velocities, which are the same slopes, and the observational model will hold a steady velocity like the computational one. The observational one is slightly above the computer one, obviously due to its initial force of acceleration. And over time, both lines would get larger and larger because the difference between both lines would get larger and larger. So as far as system and surroundings go, obviously the system is the marker. The surrounding is the air, lab table, and push of acceleration. The initial conditions, like we've talked about, are necessary for the computational model to actually be formulated. These include constant velocity of 0.273 meters per second, no net force, no net acceleration, and a total time interval of 1.133 seconds. Some errors are human error, obviously, modeling error, which could come from gravity, friction, air resistance, and tracking error that it did not track exactly the exact position of the marker. What if the axes on the graph were switched? The measure results would stay the same, but the slope of the line would flip to -1. That would simply be it. And what does this mean? In theory, there could be many different forces acting to create a force of net zero. The only forces that we can assume are gravitational force, air resistance, and friction. Thank you.